Welcome to the new era of video creation with Biozy. This is our new series on teaching deep learning. Today, we will discuss the neural network in AI. Here are the contents. Neural networks are a class of algorithms modeled after the human brain. They consist of layers of interconnected neurons, each processing data through mathematical computations. The power of neural networks comes from their ability to learn from data and adjust themselves to improve predictions or classifications. In AI, neural networks are essential because they can solve complex problems in fields such as image recognition, speech processing, and autonomous systems. The architecture of a neural network consists of multiple layers: an input layer, hidden layers, and an output layer. During training, the network learns to adjust the weights of these connections to minimize errors. Neural networks have become integral to modern AI, powering systems like self-driving cars, recommendation engines, and virtual assistants. Neural networks are composed of neurons arranged in layers. Each neuron receives inputs, processes them, and produces an output. The input layer receives raw data and passes it to the hidden layers, where the real processing occurs. These hidden layers compute intermediate values that ultimately lead to the output layer, where predictions or classifications are made. Each connection between neurons has an associated weight, representing the strength of the connection. Additionally, each neuron has a bias that allows the network to shift its activation functions output. Activation functions, like ReLU, sigmoid, and TNH, introduce non-linearity, allowing the network to model complex relationships between inputs and outputs. Without activation functions, the network would be limited to linear transformations and could not handle tasks requiring pattern recognition. There are several types of neural networks, each suited to specific kinds of tasks. The most basic type is the feed-forward neural network, FNN, where the data flows in one direction from input to output, and the neurons are organized in layers. This is useful for general classification and regression tasks. Convolutional neural networks, CNNs, are specialized for image and video processing tasks. They utilize convolutional layers to detect spatial hierarchies in data, such as edges or textures in images. Recurrent neural networks, RNNs, are designed for sequential data, like time series or natural language processing, where the output at a given time step depends on the previous one. Lastly, generative adversarial networks, GANs, consist of two networks, a generator and a discriminator, that work against each other to produce high-quality synthetic data, such as realistic images or music. Forward propagation is the first stage in the neural network's operation. It begins when data is fed into the input layer. Each input is weighted and combined with a bias term, which is then passed through an activation function, like ReLU or sigmoid, to introduce nonlinearity. This process occurs in each hidden layer until the final output is generated in the output layer. The output is the network's prediction, whether it's a class label in classification tasks or a continuous value in regression tasks. Forward propagation is critical for making inferences once the network has been trained. The main task here is to compute the network's response to the input data, which will later be compared to the actual output to compute the loss. The loss function is a key element in the learning process. It quantifies how far the network's predictions are from the actual targets. The most commonly used loss function in regression tasks is mean squared error, MSE, which calculates the squared difference between the predicted value and the true value. In classification tasks, cross-entropy loss is more appropriate as it measures the distance between the predicted probabilities and the actual class labels. The loss function serves as a guide during training, indicating how well the model is performing and where adjustments need to be made. The ultimate goal is to minimize this loss function to improve the model's predictions. Optimization techniques, like gradient descent, are used to adjust the weights and biases in such a way that the loss is minimized. Once forward propagation has been completed, back propagation is used to optimize the network's weights. Backpropagation works by calculating the gradient, or derivative, of the loss function with respect to each weight in the network. Using the chain rule of calculus, the error is propagated backward through the network, starting from the output and moving towards the input layer. Once the gradients are calculated, the weights are updated using an optimization algorithm like gradient descent. Gradient descent works by adjusting the weights in the direction of the negative gradient, effectively reducing the loss. Stochastic gradient descent, SGD, is a variation of gradient descent where weights are updated after each training example or small batch of data, often resulting in faster convergence and better generalization. Activation functions are crucial for introducing non-linearity into neural networks. The sigmoid function was one of the earliest activation functions and outputs values between 0 and 1, making it suitable for binary classification tasks. However, it suffers from the vanishing gradient problem, where the gradients become too small to update the weights effectively during backpropagation. ReLU, rectified linear unit, has largely replaced sigmoid due to its simplicity and effectiveness. ReLU outputs 0 for negative values and passes positive values unchanged, which allows the network to learn faster. The tan function, which outputs values between 1 and 1, is another popular choice, but it also suffers from vanishing gradients. Leaky ReLU is a variation where small negative values are allowed, helping to mitigate the dying ReLU problem, where neurons can become inactive during training. Training neural networks requires careful preparation of data. This often involves normalization or standardization, where data is scaled to ensure that all features contribute equally to the model. Additionally, data splitting is important, typically dividing the dataset into training, validation, and test sets. Overfitting occurs when a model learns too much from the training data, capturing noise rather than generalizable patterns. Underfitting happens when the model is too simple to capture the underlying data patterns. Cross-validation is used to evaluate the model's performance on different subsets of the data, helping to prevent overfitting and ensure that the model generalizes well. Performance metrics such as accuracy, precision, recall, and F1 score are used to evaluate the quality of the model after training. Optimization algorithms play a crucial role in how efficiently a neural network learns. Gradient descent is the most basic method for optimization, where weights are adjusted based on the gradient of the loss function. However, for large datasets, mini-batch gradient descent is often preferred as it processes data in smaller batches, improving both the speed of training and the model's ability to generalize. The Adam optimizer is one of the most widely used optimization techniques, combining the benefits of gradient descent with momentum. It adjusts the learning rate based on both the first and second moments of the gradients. Other algorithms, like AdaGrad and RMSProp, adjust the learning rate during training to improve convergence speed, especially in the case of sparse data or non-stationary environments. Regularization is a technique used to prevent overfitting and ensure the model generalizes well to unseen data. L1 and L2 regularization add penalty terms to the loss function based on the magnitude of the weights. L1 regularization encourages sparsity by driving some weights to 0, effectively performing feature selection. L2 regularization discourages large weights, preventing the model from becoming overly complex. Dropout is a technique where random neurons are dropped during training, which forces the network to rely on different combinations of neurons and prevents overfitting. Early stopping monitors performance on a validation set and halts training when performance starts to degrade. Batch normalization standardizes the inputs to each layer, which helps accelerate training and improves convergence. CNNs are specialized neural networks designed for image processing tasks. They use convolutional layers that apply filters, also called kernels, to input data to detect various features like edges, textures, and patterns. This is followed by pooling layers, which reduce the spatial dimensions of the data, making it more computationally efficient while retaining important features. CNNs excel in tasks like image classification, object detection, and segmentation. By hierarchically learning more complex features as the network deepens, CNNs have revolutionized fields like computer vision, self-driving cars, and facial recognition. Some well-known CNN architectures include LeNet, AlexNet, VGGNet, and ResNet. RNNs are designed for tasks that involve sequential data, where the current output depends on previous inputs. RNNs have feedback loops that allow information to persist, making them ideal for tasks like time series forecasting or natural language processing. However, traditional RNNs suffer from issues like vanishing gradients, which make it difficult to learn long-term dependencies. To solve this, long short-term memory, LSTM networks were developed. LSTMs introduce memory cells that allow the network to store and access information over long time periods. RNNs, particularly LSTMs, are widely used in applications like speech recognition, text generation, machine translation, and sentiment analysis. GANs are a unique type of neural network where two networks, one generating data and the other evaluating it, compete against each other. The generator network creates synthetic data, such as images, while the discriminator evaluates whether the data is real or fake. Through this adversarial process, the generator gradually improves its ability to create realistic data. GANs have been revolutionary in the field of generative modeling and have been used to create realistic images, videos, and even music. They are widely used in art, content generation, and image enhancement tasks, and have applications in fields like gaming, film production, and drug discovery. Training neural networks comes with several challenges. One of the most critical factors is the quality and quantity of data. Neural networks require large amounts of high-quality data to generalize well. Insufficient data can lead to overfitting, while biased data can result in unfair models. Another challenge is model complexity and interpretability. As models grow deeper and more complex, it becomes harder to understand how they arrive at specific decisions, which can be problematic in areas requiring transparency, like healthcare. Additionally, neural networks often require significant computational resources and time, particularly when training deep learning models. Lastly, there are ethical concerns regarding the use of neural networks in decision-making, such as bias in AI systems or the use of synthetic data generated by models like GANs. The future of neural networks holds exciting possibilities. Explainable AI, XAI, aims to make neural networks more transparent, helping us understand how models arrive at their decisions. This is especially important in fields like healthcare and finance, where decisions need to be explainable. Neural architecture search, NAS, is an emerging field where algorithms are used to automatically design the best network architecture for a given problem, significantly speeding up the model-building process. Quantum computing is expected to revolutionize neural networks by offering unprecedented computational power, enabling more complex models and faster training times. Finally, as AI continues to evolve, ethical AI development will play a crucial role in ensuring that neural networks are designed to be fair, transparent, and accountable.